Welcome to the deep dive. Today we are tackling something pretty specific, dense even. We're diving into the National Electrical Code, that's NFPA 70, the 2023 edition. And we're hunting for this fascinating statistical shortcut hidden deep inside our mission, to decode the rules governing electrical capacity for really big multi-unit buildings. Ever wonder how huge apartment complexes don't need like their own power plant? Well, the answer is in calculated efficiency. We want to understand how the experts get beyond just simple addition, how they actually apply, almost behavioral science to electrical engineering.
And it's not just a suggestion, it's mandatory. When we talk about sizing the main service, the big conductors, the transformers for these large projects, the code is very specific. It dictates exactly how you figure out the minimum safe capacity. And if you're involved in planning these projects, well, these rules directly impact costs, the amount of copper you need, and crucially, safety. It all comes down to this.
Okay, so let's start with the map, the structure of this rulebook. The NEC, we know it's vast. It covers everything, right? Chapter 1 is general stuff. Chapter 8 deals with communication systems. Chapter 3 is wiring methods.
Right. It covers a huge amount of ground. Chapter 4 for general equipment, Chapter 5 for special places, Chapter 9 has all the reference tables.
But for what we're interested in sizing that main service for a residential complex, we need to zoom in.
We do. We need to focus on Chapter 2, which is titled Wiring and Protection. This chapter really lays the foundation for delivering power safely. And crucially for our chat today, it contains Article 220.
Article 220.
Yes, which is all about calculations. Branch circuits, feeders, services, the whole calculation process starts here. And within Article 220, that's where this engineering efficiency really kicks in.
Right, makes sense. Capacity and safety grounded in Chapter 2.
Yeah.
So let's get straight to it then. Section 220.84, optional calculations for multifamily dwellings. Okay, let's unpack this. Why optional? Why not just add up every single possible load, every dishwasher, AC unit, light bulb, wire it for the absolute max? Isn't that, the safest way?
Well, that's the logical first thought, isn't it? But the answer really involves both physics and, frankly, economics. If you actually calculated the service, assuming every single load in every single apartment was running full blast all at the same time, you would just massively overestimate the real need. I mean, wildly overestimate.
Little much.
Think about a 100-unit building. Your calculation might spit out something like, 10,000 amps.
Wow.
Yeah. You'd need transformers and service gear size for a pretty large industrial facility. It's just unnecessarily huge, enormously expensive, and often physically impractical to even install. So the optional calculation exists because the engineers, the code writers, they know that human behavior diversifies the load. It spreads it out. People just don't all decide to run their microwaves and their washing machines and their dryers and their electric stoves precisely at 7:00 p.m. on a Tuesday. Doesn't happen.
So the optional calculation is really the code saying, okay, we acknowledge reality, we acknowledge diversity.
Right.
But before we get to that diversity factor, the code draws a clear line, doesn't it, between different types of power needed in the building?
Oh, absolutely. Very clear. Section 220.84b specifically addresses what it calls house loads.
House loads.
Right. These are the loads for the common areas, the non-residential parts. Think elevators, hallway lights, maybe lobby air conditioning, central heating systems if they have them, outdoor lights, security systems, that kind of thing.
Okay, the building's own systems. And these loads don't get the benefit of this optional diversified calculation.
Correct. The code is very explicit. It says these house loads have to be calculated separately following Part 3 of the article, and then they get added in addition to the calculated load for the dwelling units themselves.
In Part 3, that's the standard calculation. No diversity factor applied there.
Exactly. Part 3 is the standard, more rigid, non-diversified calculation method. You generally have to assume those shared systems could run at their full potential, so you have to wire them to handle that maximum possible draw.
Okay, that distinction is really important. So standard calculation for the building's own fixed stuff, the house loads. Then you get to apply this statistical shortcut for the, let's call it the human factor, inside the actual apartments.
Yeah.
Which brings us to the really fascinating part. Here's where it gets really interesting. The efficiency mechanism itself.
Right. Now we arrive at Table 220.84b. The title is Optional Calculations Demand Factors for 3 or More Multifamily Dwelling Units. This table, this is basically the codified statistical model of how people use electricity in groups.
Demand factor. So that's the key term. It's basically the percentage of the total possible load you actually need to design the system for.
Precisely. You calculate the theoretical maximum, every outlet, every appliance. Then this table gives you a percentage, the demand factor, based on the number of units. And that tells you the actual minimum capacity the service needs to handle.
And what's wild is, like you said, this table is essentially codified sociology. It's data on energy use patterns turned into a rule.
That's a great way to put it. The underlying logic is pretty straightforward. The more apartments you have, the lower the chance that a high percentage of them will be demanding maximum power all at the same instant.
So more units equals lower probability of peak overlap.
Exactly. Therefore, as the number of units goes up, the required capacity, the demand factor percentage, drops, sometimes quite dramatically.
Let's look at how steep that drop is. Give us some examples from the table. If you're building something small, say just 3 to 5 units.
Okay, for 3 to 5 units, the code assumes the overlap in usage could still be fairly high, so the demand factor is 45%.
45%. So nearly half of the total theoretical load.
That's right. Now, compare that to a bigger building. Let's jump ahead. Once you hit 21 units,
Okay, 21.
the factor dropped down to 37%.
Wow, okay. From 45 down to 37, that's an 8 percentage point drop already.
And think about what that means, that 8%. Applied across the total potential load of 21 apartments. That represents a really significant saving.
In what specifically? Just wire size?
Well, yes, conductor size, but also potentially the size of the main transformer, the switchgear. We're talking serious cost savings in copper and equipment. You're buying substantially less infrastructure.
Can you give us a sense, even ballpark, of what dropping from, say, 45% down closer to 30% might mean financially on a large project? It's not trivial, is it?
Oh, not at all. It's major. Think about the main service entrance conductors, those big cables coming in, and the utility transformers maybe feeding the building. These are big-ticket items, capital investments. So dropping from 45% down to 30%, which, by the way, the table says happens when you get to 34 to 36 dwelling units.
Okay, 30% at 34 units.
Right. That means your required service rating is literally a third smaller than if you had, say, built 9 separate 4-unit buildings and calculated each one individually using that 45% factor. The savings can easily run into the tens of thousands of dollars, sometimes much more, just on the electrical infrastructure cost, both for the developer and sometimes for the utility providing the power.
That's where the engineering gets really compelling, isn't it? It's a massive financial nudge built right into the safety code, favoring larger, denser projects, all based on trusting statistics about human schedules.
And it keeps going down. The efficiency gain continues. For instance, for complexes with 51 to 55 units, the calculated demand factor is only 25%.
25%.
A quarter.
A quarter of the theoretical maximum. The code is basically trusting, based on historical data and probability, that with 55 different households, the sheer randomness of their daily routines virtually guarantees the peak loads won't align often or severely enough to overload a system designed for 25%. So we've gone from needing almost half the potential capacity at just 5 units, all the way down to just a quarter of the capacity at 55 units.
Amazing. So where does it bottom out? What's the point of maximum efficiency according to the code? Is there a floor?
Yes, the table provides a hard floor. The absolute minimum calculated demand factor, according to Table 220.84b, is reached for complexes that have 62 or more dwelling units.
2C2 and over.
At that point, the demand factor hits its minimum and plateaus at 23%.
23%. And it doesn't go any lower, even if you have 100 units or 200 units.
Correct. It stays at 23% for 62 units or more. And if we connect this to the bigger picture, there's a reason it flattens out there.
By the time you've accounted for the diversity across the first 62 units, you've already captured most of the statistical benefit. The diversified load calculated for those first 62 units becomes a significant sort of fixed baseline portion of your total calculated load. Adding more units beyond 62, well, their diversified usage is assumed to just mirror the pattern you've already established. You don't gain much additional percentage efficiency. You've essentially maxed out the statistical advantage the code allows for diversification at that point.
23%. That's the magic number for large complexes. Okay, so let's quickly summarize this deep dive for you listening. We jumped into Chapter 2 of the National Electrical Code, Wiring and Protection. We found this really sophisticated technical shortcut, the optional calculation in Section 220.84. And this formally recognizes how people actually use power in large groups, in multifamily dwellings. It allows the electrical design to dramatically reduce the required capacity based on the number of units using the demand factors in Table 220.84b. dropping it all the way down to just 23% of the theoretical maximum load for the biggest projects, 62 units and up.
Exactly. And it really illustrates that these codes, these rule books, they aren't just dry lists of materials or installation methods. They're living documents. They're rooted in applied statistics, in probability, in understanding real-world behavior to achieve calculated efficiency. It lets us build denser housing, more affordable infrastructure without actually compromising safety, all because the engineering trusts the math behind diversified human behavior. But, relying on these statistical models established in the 2023 code at 23% for large buildings does raise a really interesting question for you to think about. We're seeing rapid electrification. Think electric vehicles becoming common, everyone potentially plugging in their car when they get home around the same time. Think about people switching from gas stoves to powerful induction cooktops. Could these trends towards high-draw electric devices, maybe used more simultaneously than in the past, start to challenge the core assumption of diversity that gives us that 23% factor? I mean, if usage patterns do become more synchronized, less diversified in the future, what happens then? What hidden infrastructure cost might that create down the road, forcing upgrades to systems that were originally sized assuming only 23% of the potential load would ever be needed? Something to consider.